So what have we done to this point? We said that what we see is the speed of the bar is some number bigger than 0. So v bar is some number bigger than 0, and that implies that the force on the charges is magnetic. Now, what would the insect see? So the insect rides along on the bar, and so the insect does not see the charges moving at any moment. So the insect would say the speed of the bar and the charges in the bar is 0. So we said that we claimed that the force that the insect sees is the electric force. So F, the force, is electric. And we gave a very loose argument for that because we notice we have a change in magnetic flux over change in time. The rate of change of magnetic flux is F over Q. And we remember from chapter 16 that F over Q is electric field. So let's explore this a little bit more and see if we can convince ourselves that from the insect's perspective, the force on the charges is the electric force. So if I were to write the rate of change of magnetic flux as negative E times Y, and if I think about this for a moment, the right side of this equation looks very similar to something else we saw in now chapter 17. In chapter 17, you saw V equals negative ED, where we have a voltage and the potential difference between two locations is the strength of the electric field times the distance between those locations. Well, this looks very similar to what we have up here. We have something that looks kind of like a voltage on the right-hand side. And it turns out that this term here actually is a voltage. So this is a voltage. Now, if we go back to think about why do currents flow around wires? So this was the beginning of chapter 18. The way you get charges to move in a wire is you have to push on them. In order to push on them, you have to set up an electric field to get the charges to move. What happens is a battery is a source of voltage. That voltage I could think of as kind of like it sets up the electric field that causes the charges to move around the wire. So what we have here is the changing magnetic flux is creating a voltage, and that voltage is going to cause the charges in the wire to see an electric field and begin moving around. So the changing magnetic flux is going to induce an EMF. An EMF, as we said, for the context of this course, EMF is just voltage. I am going to write EMF here so I match what is written in the textbook. So what we see depends on our perspective. Now, one of the rules of special relativity is every non-accelerated observer should see the same physics. So, and I could write from special relativity, every non-accelerated observer should see the same physics. So we are not an accelerated observer. We are standing here watching the bar move, and we see the charges being pushed downward. And we would say, okay, after the bar has traveled this distance, a charge that was up here went down to here. The ant is traveling on the bar, and the ant has moved with the bar. The ant doesn't see the charges moving to the left or to the right, but the ant must also agree with us that at one moment a charge was here, now it's near the bottom of the bar. The ant and us are not allowed to disagree on the location of the charges, but we are allowed to disagree on the nature of the force that is pushing on those charges. So we see a magnetic force pushing the charges down. The ant sees the electric force pushing the charges down. And both of those perspectives are correct. They're just seeing the same physics from two different points of view. So the electric force and the magnetic force are, on a fundamental level, the exact same force. They're just seen from different perspectives. So there is a very intimate connection between electricity and magnetism. I find that we disagree with the ant on the nature of the force that is pushing on the charges. And as we said, one of the postulates of special relativity is that every non-accelerated observer should agree on the same physics. And if you ever need a good $37 word, a non-accelerated observer is also known as an inertial observer. So ultimately, what did we find in this thought experiment? What we did was we moved a bar that contains charges, and we found that there was a force on the charges inside the bar. Now, this force will cause the push on the charges, so ultimately we'll see when we begin working with the PowerPoint slides that when the charges are pushed, they're going to move, and what we're going to do is this is going to create a current inside the bar. Now, we'll talk about this more formally in a future video. Well, in order to get a current, you need to get a voltage because V equals IR. Well, voltage is basically the same thing as EMF for the purpose of what we do in this course. So we found that a changing magnetic flux will create an EMF. And EMF is basically, like I said, for the purpose of what we do, we could think of this as a voltage. So a changing magnetic flux through a loop of wire will create a voltage. That voltage will create a current. And so it's possible to get current flowing in a loop of wire without any battery present. All you need to do is you need a changing magnetic flux. So I want to point out that there is the notion of magnetic flux, which is phi b. There is a change in magnetic flux, which is delta phi b. And then there is a rate of change of magnetic flux. Which is delta phi b delta t. And I just want to take a moment to quickly point out these are three different things. So be careful when you're doing problems, don't mix them up. Anytime a quantity changes, implicitly you're saying you have an initial and a final value, and nothing will be able to ever change instantaneously. It does take time for a quantity to change. So the rate of change of magnetic flux is, we say, induces an EMF. So the rate of change of magnetic flux will basically create a voltage. Now, later on, we will have a rule for will this induced EMF, will this created voltage tend to make the current flow clockwise or counterclockwise around this loop. We will address that problem in the future. But for now, the punchline of this thought experiment that we created was it is possible to create voltage by having a changing magnetic flux.